We are Merkutech aviation team from Istanbul Arel University. This is our team that competing over than 2 years. This is our competition team who will carry out the SUAS 2024 mission. To successfully complete the competition task, the drone must be able to complete the entire task within 30 minutes and have more than 20% battery charge remaining at the end. For this reason, our aircraft is designed to have a speed of approximately 10 miles per hour. The drone must maintain stable and secure flight throughout the mission while fully loaded. To achieve this, automatic and manual PID configurations were implemented for the drone. Harmonic and PES filters were fine-tuned to minimize vibrations and clipping on the flight controller, and position accuracy was maximized. Barometer and temperature calibrations were performed to increase the drone's altitude accuracy on the Z-axis. Additionally, rangefinder-based altitude detection was developed to enable precise takeoff and landing. Drone must capture high-quality images for the ODLC task. Therefore, a custom gimbal was designed to allow the drone to take stable images even at high speeds. The drone must identify the locations where it will drop the payloads for different loads. For this purpose, software was developed that can distinguish colors, shapes, and features on objects. Drone must drop a total of 5 payloads to specific locations with a maximum deviation of 20 feet. Therefore, the drone is designed to carry the maximum possible payload. The specially designed payload drop mechanism minimizes cost and maximizes load drop accuracy. Additionally, GPS is supported using the RTK and NTRI protocol for high position accuracy.
We have designed a two-step pipeline for ODLC. YOLO detects the shapes in the first step, while the second step handles OCR and color detection. The crucial aspect of this design is that process 2 only executes if process 1 succeeds, leading to significant improvements in performance. We initiated our dataset with 400 images, focusing only on shape detection. After that, we applied augmentation processes, expanding our dataset to approximately 3600 images. To further enrich our dataset scope, we integrated it with available public datasets. We choose YOLO for its state-of-the-art speed and accuracy in real-time object detection tasks, making it perfect for this mission where speed is crucial. For the model size, we choose YOLO V8S over YOLO V8N due to its significant accuracy improvements despite a slight decrease in FPS. Initially, we apply necessary thresholding and masking methods to break our detection bugs into 3 regions. This process leaves us with background, shape, and character. We determine the color of the object by passing the average RGB values of the white areas to our lookup table. Then, for the OCR part, we have tested several OCR methods, including Tesseract, EasyOCR, and OpenCV's hue moments. Following the tests, EasyOCR emerged as the top performer for letter recognition, by beating both at inference time with a slight decrease at accuracy. For the localization, we use the FOV algorithm and determine the object positions based on our drone's GPS data. After that, we use MovSDK API to guide the drone to target locations and perform drops on the objects.
We prefer the 22,000 mAh LiPo battery for our UAV. According to our flight time calculations, it can fly in the air for 52 minutes.
The hexacopter has designed for both capable of carrying the required payload for a specific duration and ensuring safe and stable flight. The UAV's body consists of 2 carbon fiber plates stacked up each other. The lightweight yet durable nature of carbon fiber prevents deformation caused by external forces acting on UAV's body. The motors of the hexacopter are attached to the drone using carbon fiber pipes. During the selection process of these pipes, priority was given to minimizing deformation resulting from forces acting along the carbon fiber and its link to the body. Optimal values were determined through experimentation with experimental data. To enhance stability and minimize both bending and twisting moments, the carbon fiber pipes of the hexacopter are attached to the body with aluminum mounts. The hexacopter is powered by the T-Motor MN6007 with 18-inch carbon fiber propellers attached to the motors.
RTK, real-time kinematic, is a technology that allows drones to determine their position with much higher precision than standard GPS. Since positioning is extremely critical in our mission, especially for waypoints, we aim to achieve much more precise positioning using RTK.
The UAV we designed has a high capacity to carry any given payload, and it also designed to execute both drop and fly in a safe and stable way. In order to deliver the payload gently, we designed a payload mechanism with only one servo and two pulleys. The payload mechanism is mounted to a blade and it has two pulleys with a string wrapped around them, montage front and back of the plate. A special clutch system attached on the top of the grooves that allows us to change the sensitivity of the mechanism, thus enabling us to adjust the drop timing and the horizontal speed of the payload. When ODLC system detects the password, it sends two different PWM signals to servo, and depending on the password that has been detected, the required pulley activates and delivers the payload.
As a result of our comparisons made for autonomous flight, Pixar's Orange Cube was chosen. Pixar's Orange is a high-performance flight controller designed to manage the complexity of autonomous flight. RTK, real-time kinematic, is a technology that allows drones to determine their position with much higher precision than standard GPS. Since positioning is extremely critical in our mission, especially for waypoints, we aim to achieve much more precise positioning using RTK. The ground station will be used to interact with the UAV. The mission planner, developed specifically for autopilot, is designed to monitor the UAV's flight controls, autopilot system, and many features in real time from the ground. During the flight, it is necessary for the drone to avoid obstacles. To implement this process, we placed a total of 6 ultrasonic distance sensors at 6 different points on the drone. We preferred the band ruler algorithm to process the data from the ultrasonic sensors and create a route. The algorithm continuously monitors the data from each sensor, and if an obstacle detected, it calculates a new route for the drone to safely avoid obstacles. This route calculation process is performed using specific trigonometric and vectorial formulas. The band ruler algorithm and sensor data are integrated into the flight control software, the Pixar Orange Cube. Tests conducted in simulation and the field demonstrate that the systems yield successful results. Our communication system consists of telemetry and radio receiver. Our telemetry, the encrypted communication version of the RF module, can encrypt command or telemetry data. The RF module uses frequency hopping spread spectrum, FSK modulation, and automatically selects the best frequency band for reliable communication. It has a range of 40 km in open areas and 1 km in urban areas, providing high data rates. The RF module operates in 900 or 900 MHz frequency band and supports the Mauling protocol. Our radio receiver and controller operates in the FRS frequency range with high precision filters for radio safety. Adjustable antenna length can work within the 2.4 GHz range. The designed hexarotor stands out with a payload capacity of 44 pounds, high efficiency, and a more stable flying ability compared to the quadrotor configuration. Additionally, it offers advantages such as a wide body area, longer range, and greater payload capacity. The comparison table clearly demonstrates that the hexarotor structure is the most suitable for mission requirements. These features provide an ideal option for carrying heavy loads and conducting long-duration flights. Pre-flight and post-flight quality control and feedback forms are used for hardware improvements. Equipment used in production is regularly calibrated and maintained. Stock orders for imported parts help prevent delays in the procurement process. Designs are validated through analysis and prototype testing during the design process. After test flights, RSSI values are checked to determine the correct antenna position in order to prevent telemetry signal losses. The RSSI distance is monitored to maintain the controller connection, and the drone is safely brought back before the connection is lost. Additionally, the quick change structure allows easy removal and assembly in case of airdrop errors. To prevent IMU errors, necessary calibrations are performed before flight, and noise filtering parameters are improved by reviewing log data after flight.
We found the middle way by using two different processes. By running YOLO in first and the OCR and color detection in second process, we are giving each process its own memory and resources. This ensures our both core functions are separated, doesn't directly interrupt each other, and still stay connected for an affordable performance trade-off. We use YOLO with TensorRT, which is specifically designed for NVIDIA GPUs to enhance the performance of machine learning models. Using TensorRT accelerated our inference time by up to 38% and reduced our memory usage around 23%. For the system design, we have tried three different approaches. Synchronous approach is beneficial when it comes to memory safety and simplicity. By ensuring every task is executed at a time, it minimizes the chance of memory corruption and helps debugging to be easier, but it comes with a performance trade-off. Executing 3 tasks at a time constantly is unneeded and consumes our resources significantly. This can be prevented by running the threads conditionally based on which operation we need, but it adds too much complexity to the code due to drone movements is done with async functions.
We conducted various tests to test our communication system. We flew our drone in different weather conditions, behind physical obstacles, and at long range. As a result of these tests, our communication system provided successful results.
Through repeated testing, the mechanism operated as intended, ensuring both the safety and gentle delivery of payloads. The success rate of this test has been notably high with landing parameters continually.
To demonstrate the durability and stability of the finalized drone design, extensive static and flight tests were conducted. These tests involved 20 flights with a total duration of 150 minutes. 18 of the flights were completed without airdrops, while the remaining 2 were carried out with a full payload. During the tests, the maximum turn deviation rate was carefully monitored and verified. It was observed that the drone could consistently maintain stable flight for over 45 minutes at its average cruising speed. During the flight, we performed aggressive maneuvers and sudden corrections to test stability and accuracy of the autopilot. As a result of the tests, the autopilot provides stable results at a sufficient level for waypoint mission. The main reasons for the high level of success in the tests were the internal calibration and manual configurations performed. Our drone has been subjected to numerous tests, both in simulation and in real environments. As a result of these tests, results that can be considered successful were obtained as seen on the screen. It is accepted that the success rate of the results will increase until the competition date. In the first flight, the drone was taken 1,000 feet away from the pilot with safety pilot control and safely brought back for landing. In the second flight, the drone was manually lifted off with safety pilot control and an auto mission was initiated. With the auto mission, the drone went 200 feet away from the safety pilot and returned. After completing the mission, the drone was safely landed with pilot control. In the third flight, an auto mission was defined for the drone cover a total of 8 miles as part of the competition requirements. Then, the drone was autonomously lifted off and the mission was initiated. After completing the mission, the drone safely landed with manual control. In this video, we provide a detailed explanation of all technical details of the drone we developed this year. With the results we have achieved, we are aiming for high performance and success in the line with the task. We wish all competitors the best of luck.